and welcome to another lesson at EDU Solutions Institute. So today we're looking at the IB Physics syllabus, but we're going to recap on some motion topics, and we're going to do two questions to help us to put into practice what we were taught in regards to motion in the IB syllabus. So if we go now to this question that says, Lucy stands on the edge of a vertical cliff and throws a stone vertically upwards. The stone leaves her hand at a speed of 50 meters per second. At an instant, her hand is 80 meters above the surface of the sea. Air resistance is negligible, and the acceleration due to gravity we're going to use as 10 meters per second squared. Calculate the maximum height reached by the stone as measured from the point where it was thrown. So this here is an example of motion, and specifically vertical motion, where it's gravity that is the forefront of the force acting on this object. So hence we will look at free fall. So what we're going to do is we're going to take and identify what we're given. So we're given that it starts off with a velocity of 50 meters per second. That's u, right? We're also given that a, it's accelerating, it's going up, so therefore it's slowing down. So we're going to use a negative meters per second squared to indicate that it is slowing down, it's decelerating, right? We also know that when it reaches maximum height, its velocity would be 0 meters per second. So now we have three things, and we need to know what S is for this first part. So let's go ahead and we find S, right? Based on our formulas, we don't have time, so we can use this motion equation without the use of time. So we put in V, which is 0 squared, U, which is 15 squared, plus 2 times A, which is negative 10, multiplied by S. Right? When we put that in your calculator, we will get an answer of 11.25 meters. And we always use the smallest significant figure we inputted from our measured value, which would be, or from the given values, which would be 10, which is 1 sig fig. So therefore, we round this off to 10 meters. All right, next part we say is that to determine the time for the stone to reach the surface of the sea after leaving Lucy's hand. So in this case, because we're going to find the time to go up and add it to the time to go down, right? So let's do time to go up. And time to go up, we can use a formula that's V minus U over A, which makes it V, which is 0, minus U, which is 15, over minus 10, we get 1.5 seconds. Right? Now coming down, so T down would mean that it starts, let's write down what we're given. It starts from 0 because it's at its maximum height, coming down now. Its acceleration will be a positive 10 because it's speeding up, coming down. Right? What else do we know? We also know the distance that it's coming down to reach the sea, which would be the 80 plus the 10, which is 90 meters. All right, so we can find T by using S is equal to UT plus half AT squared. We do not have U, so therefore U is 0, so that means that part is 0. So we put in 90 for the S, half of 10 multiplied by T squared. So therefore we get T to be, so it's 90 divided by 5, which is 18. Then we square root 18, which gives us 4.2 seconds. So therefore the total time would be 1.5 to go up and a total of 4.2 to come down. So that gives us 5.7 seconds. And again, we put in our smallest sig figs, which is 1, so we get 6 seconds. For this question, all it took part for us is to understand the principle of free fall, which always means that the acceleration is 10. So it's either it's negative 10 when it's slowing down, or it's positive 10 when it's speeding up, right? Once we understand that principle and we break up the motion in terms of moving up and coming down, we can answer any free falling question. Right. Next question is still on motion, where it states that state the difference between average speed and instantaneous speed. Now we can say that average speed, let's call it AVG, is the total distance over the total time. And what this means is if we consider all the distance that an object moves and divide it by the time it took to move that distance, we get the average speed, which means the object went above this value at some point and it went below this value at some point. So that's why it's an average, right? And then we look at the instantaneous speed, which is basically tells us it is the speed at a given point, right, or a given time. So if we want to know what's the speed at this specific period of time, then we're finding that instantaneous speed. While the average has to consider all the different motions, when it speed up, when it slows down, and we average that to give us one value to say that the object was moving from this distance with this average speed. All right, part B. The graph shows an acceleration of a particle varying with time. Time t equals 0, the instantaneous speed of the particle is 0. Calculate the instantaneous speed of the particle at t equals 7.5 seconds. Right? Now, what we should note from an acceleration time graph is that if we want to find the speed, we will do the area under the line. So if we take the time that it's stated here, 2, 3, 4, 5, right? We cut it right here at 7.5, right in the middle here, where it's going to stop right there. We're going to find this area, right? That's a triangle. So we would go with the instantaneous speed, let's call it, that is equal to half the base times the height. So the base is 7.5 seconds, and the height would be this point, which is at 3 meters per second squared. So therefore, that value would be 11.25, right? Which is rounded off to 1 sig figs, which would be 10 meters per second. That would be your instantaneous speed at that given specific point. All right, let's go with the next part. It says using your axis, show or sketch a graph to show how the instantaneous speed of the particle varies with time. So here we note that the velocity or the acceleration is a constant increase or uniform increase. Let's use the word uniform in this motion. So what that means is that the speed is also changing at the same rate as which the time is changing. So therefore, we can always just use a line like that, which shows us a straight line gives us that the acceleration is a constant, right? Now, it's going to be slightly different here, sorry, not a straight line. What it tells us is that the instantaneous speed at every given time would be increasing with time. So therefore, you'll get the straight line graph like that. All right. Next part is the graph shows that the variations are with time of the speed v of the ball of mass 0.50 kilograms that has been released from rest above the Earth's surface. The force air resistance is not negligible. Assume that the acceleration of free fall is 9.81 meters per second squared. Stay with our calculation how the graph should be used to determine the distance falling. So this is the velocity time graph, and therefore to find the distance, we would find the area under the line. So area under the line will give us the distance that was traveled. Next part is in the space below, draw an arrow to represent the forces on the ball at t equals 2 seconds. So if we look at t equals 2 seconds, it is still increasing in speed. So therefore, what we will note is that there would be a force from the center of the ball going down, which is called your weight, and also you will have the force going up from your air particles, which is smaller than your weight value, and that is your air resistance. Right? It's smaller because the object is still accelerating, it's still speeding up. So therefore, weight has to be greater than the air resistance. So use the graph opposite to show the acceleration of the ball at 2 seconds is approximately 4 meters per second squared. So we're going to prove that the acceleration here is at 2 seconds is 4 meters per second squared. So at 2 seconds, the first thing is to note is to find the velocity, which is at this line here, which is going to be 40. All right. So at 2 seconds, its velocity is at 14 meters per second. Right? Now we need to prove that its acceleration is at 4 meters per second squared. So let's see what other thing that was given here. It says that its mass is 0.5 meters per 0.50 kilograms. All right. So if we look, we have 0.5 kilograms. We have G, which we can find the weight. Right. So what we're going to do is, because it is on a curve, we are going to do a tangent. Right. So if we do a tangent right at 2, see how best I can get this to be a tangent. So at the 2 seconds, we are going to draw a tangent. Very good. And we find the gradient of that tangent. Right? So we're going to use this point here, which is 17. And we're going to use this point here, which is 13. And that 13 is with 7. And the 17 is with 2.3. Well, 2.6. Right? So we go with the gradient m, which is change in y over change in x. So the change in y would be 17 minus 13. Let's just double check again. It was 13. Wait, no, it was 12, sorry. And 17. So 12 and 17. And the change in x was from the 17, it came down to the 2.6, and then this one was 1.4. 1.4, 2.6. So we have 5 divided by, this would be 0.6, 0.6, which is 1.2. So 5 divided by 1.2 That gives us 4.16, which rounded off to one sig fig is 4. All right. And then we are going to end right here because everything else would be in addition to forces, right? And which we will continue this in our next lesson for next week. So thanks for watching. Hope you understand how to use these motion equations and a little bit about motion in a practical sense. Thanks for watching and I'll see you next week.